So here's something that might seem a little strange to think about as you're lying there, getting comfortable, letting the day wind down. The universe, at its most fundamental level, follows rules. Precise, mathematical, unbreakable rules. Every atom, every photon, every gravitational tug between two distant stars obeys the same equations that physicists have been scribbling on chalkboards for centuries. And yet, and this is the part that kept some of the smartest people in history up at night, the universe is also wildly, stubbornly unpredictable. Not because the rules break down, not because there's some hidden randomness lurking underneath everything, but because the rules themselves, followed perfectly, can produce behavior so complicated, so sensitive to the tiniest whisper of a difference in starting conditions, that prediction becomes practically impossible. That's chaos theory, in its bones, and I want to walk you through it tonight, slowly, from the very beginning, because it's one of those subjects that sounds intimidating, but is actually deeply intuitive once you let it settle in. It's about weather and waterfalls, and the shape of coastlines. It's about why your heart beats the way it does, and why the solar system, the very thing we think of as the clockwork model of predictability, isn't quite as clockwork as we were taught. But we'll get to all of that. Let's start somewhere quieter. Let's start with the people who thought they had the universe completely figured out. Imagine it's the late 1600s. Isaac Newton has just published his Principia Mathematica, and the intellectual world is reeling. Here is a man who has shown, with devastating mathematical clarity, that the same force pulling an apple to the ground is the same force keeping the moon in orbit around the Earth. One law, one equation, and it works everywhere for everything, from cannonballs to comets. The implications are staggering. If you know the position and velocity of every object in a system, and you know the forces acting on them, you can, in principle, calculate exactly where everything will be at any future moment. The universe is a machine. A gloriously complicated machine, sure, but a machine nonetheless. Wind it up, let it go, and its future is determined. This idea didn't just stay in physics. It seeped into philosophy, into theology, into the way people understood their place in the cosmos. And the person who stated it most boldly wasn't Newton himself. It was a French mathematician named Pierre-Simon Laplace, about a century later. Laplace imagined a hypothetical intellect. Later generations would call it Laplace's demon, that knew the position and momentum of every single particle in the universe at one instant. Given that information, and given Newton's laws, this intellect could calculate the entire future of the universe and reconstruct its entire past. No uncertainty, no surprises. Everything that will ever happen is already encoded in the present moment, if only you had the computing power to decode it. Now, that's a breathtaking claim. And here's the thing. For a very long time, it seemed basically right. The successes of Newtonian mechanics were extraordinary. Astronomers could predict eclipses decades in advance. Engineers could calculate the trajectory of a bridge load or a spinning flywheel with stunning accuracy. The mathematics worked. The predictions came true. And so a deep assumption settled into the foundations of science, an assumption so fundamental that most people didn't even think of it as an assumption. It was just obvious. The assumption was this: if a system follows deterministic laws, meaning no randomness, no dice rolling, just pure cause and effect, then that system is, at least in principle, predictable. Determinism equals predictability. And that assumption held for about 200 years. It held through the development of thermodynamics, through the harnessing of electricity, through the engineering of steam engines and telegraph lines and railways. It was the bedrock of what we now call classical physics. And it's wrong. Not completely wrong. It's right in a lot of cases, the cases that happen to be easiest to study. But as a universal principle, it's wrong. And the first real crack in it appeared in a place you might not expect: the problem of three bodies orbiting each other in space. Let me set this up for you, because it's a beautiful problem, and it haunted some of the greatest minds in mathematics. Newton's law of gravitation lets you solve the two-body problem perfectly. Take the Earth and the Sun, ignore everything else, and you can write down an exact equation describing the Earth's orbit for all time. It's an ellipse, clean, elegant, closed form. You can predict where the Earth will be 1,000,000 years from now, no problem. But now add a third body, say Jupiter. Three objects, all pulling on each other gravitationally, all moving, all changing each other's trajectories simultaneously. You'd think, given that you've solved the two-body case so neatly, that the three-body case would just be a bit harder. More algebra, maybe. A messier equation, but still solvable. It's not. The three-body problem, in general, has no closed-form solution. You cannot write down a single neat equation that tells you where all three bodies will be at an arbitrary future time. And this isn't because we haven't been clever enough. It's because the solutions are, in a very deep sense, too complicated to be captured by the kind of mathematical expressions that worked so beautifully for two bodies. The trajectories can be wildly irregular, looping and spiraling in ways that never quite repeat. Now people knew the three-body problem was hard, long before anyone used the word chaos. Euler worked on it. Lagrange worked on it. They found special cases, very particular arrangements where three bodies could orbit stably, and those solutions are genuinely useful. The Lagrange points, for instance, are specific locations in a two-body system where a third, smaller body can hang in a kind of gravitational equilibrium. There are 5 of them for the Earth-Sun system, and we actually park spacecraft at some of them today. The James Webb Space Telescope sits at the second Lagrange point, about 1.5 million kilometers from Earth, in a spot where the gravitational pulls of the Earth and Sun conspire to let it orbit the Sun in lockstep with us. So those special solutions matter enormously. But the general problem, 3 arbitrary masses, arbitrary starting positions and velocities, remained unsolved. And then, in the 1880s, the King of Sweden decided to hold a mathematical competition. Oscar II, yes, the actual king, was a patron of the sciences, and to celebrate his 60th birthday, a prize was offered for the solution to a problem closely related to the stability of the solar system. Could anyone prove that the solar system was stable? That the planets would continue orbiting more or less as they do now, forever, without one of them getting flung out into deep space or spiraling into the sun? The person who took on this challenge most seriously was Henri Poincaré, and he is, in many ways, the true grandfather of chaos theory, even though the word chaos wouldn't be used in this context for another 80 years. Poincaré was one of those figures who comes along maybe once in a generation, a mathematician of extraordinary range and intuition. He worked in topology, in number theory, in the philosophy of science, in celestial mechanics. He was the kind of thinker who could see connections between fields that other people didn't even realize were related. Poincaré didn't solve the stability problem. Nobody has, fully, even today. But what he did was arguably more important. In wrestling with the three-body problem, he discovered something that disturbed him. He found that in certain configurations, the trajectories of the bodies were so sensitive to initial conditions that the tiniest change, an imperceptible difference in a starting position, could lead to completely different outcomes over time. The paths didn't just diverge a little, they diverged enormously, and the behavior could become so tangled, so intricate, that he described it as too complex to draw. Think about what that means. Here is a system that is perfectly deterministic, no randomness at all. 3 masses, 3 gravitational forces, Newton's laws applied with perfect fidelity. And yet, the long-term behavior is, for all practical purposes, unpredictable, because you can never measure the starting conditions with infinite precision. There's always some tiny uncertainty. Maybe you know the position of a planet to 10 decimal places, or 20, or 100. It doesn't matter. Given enough time, that tiny uncertainty will grow and grow until your prediction is completely useless. Poincaré had stumbled onto the essential insight of chaos theory right there in the 1890s. But here's what's fascinating. The world wasn't ready for it. The mathematical tools to fully explore what he'd found didn't exist yet. Computers didn't exist yet. And the prevailing intellectual culture was still deeply committed to the idea that determinism meant predictability. So Poincaré published his results. Other mathematicians admired them. And then, the insight sort of went to sleep. It lay dormant in the mathematical literature for decades, like a seed waiting for the right season. And there's actually a wonderful bit of drama in the publication itself. Poincaré's original submission to the King Oscar Prize contained an error. Not a small one, a significant mistake in his analysis of the stability of certain orbits. He had initially argued that the orbits were more stable than they actually were. The error was caught by a colleague, Lars Edvard Fragman, during the review process, and Poincaré was mortified. He had to recall the printed copies of his paper, at his own expense, which actually exceeded the prize money he'd won, and publish a corrected version. And here's the kicker. The corrected version was the one that contained the really revolutionary insight. The error had been papering over the chaos. When he fixed the mistake, he was forced to confront the full complexity of what was happening in those trajectories, and that's when he realized just how sensitive and tangled they could become. So the very thing that embarrassed him, the mistake, the public correction, the expense, was what pushed him to see more clearly than anyone before him that deterministic systems could behave in fundamentally unpredictable ways. There's a lesson in that, isn't there? Sometimes the error is the discovery. But as I said, the world moved on. The early 20th century brought relativity, quantum mechanics, 2 world wars. Physics was consumed by the very large and the very small, by the bizarre behavior of atoms and the warping of space-time. The kind of classical mechanics that Poincaré had been working on, orbits, trajectories, the motion of everyday-sized objects, seemed almost quaint by comparison. It was well understood, people thought. Solved. You learned it in your second year of university and then moved on to the real frontiers. And so the seeds Poincaré had planted lay dormant through the first half of the 20th century. A few mathematicians tended them. George Birkhoff at Harvard did important work in the 1920s and 30s, extending Poincaré's ideas about dynamical systems. Mary Cartwright and J.E. Littlewood at Cambridge during World War II studied certain nonlinear differential equations that arose in radio engineering and found behavior that was, in their words, wild. Signals that should have been predictable were doing strange, almost random-looking things, and Cartwright and Littlewood proved mathematically that this was an inherent property of the equations, not a flaw in the equipment. But these were specialized results, known mainly within pure mathematics. The broader scientific community, the physicists, the engineers, the meteorologists, hadn't absorbed the lesson yet. What changed everything, what finally woke the sleeping insight up and turned it into a revolution, was a combination of two things. One was a person, an unassuming meteorologist at MIT named Edward Lorenz, and the other was a machine, specifically a Royal McBee LG-P30 computer, about the size of a large desk, with a processing speed that your phone today would find laughable. And what happened one winter day in 1961, when Lorenz sat down at that computer and decided to rerun a weather simulation, taking a shortcut that seemed completely harmless at the time? Well, that's a story worth telling slowly, because it's one of those moments where the entire direction of a science pivots on something so small, so seemingly trivial, that you almost can't believe it mattered. So here's the setup. Edward Lorenz was not a dramatic figure. He wasn't the kind of scientist who gave fiery lectures or courted controversy. He was quiet, methodical, a little reserved, the kind of person who would sit in his office for hours, staring at printouts, thinking. He'd trained as a mathematician, actually, getting his master's degree from Harvard. But then World War II happened, and like a lot of young men with mathematical talent, he got pulled into meteorology. The military needed weather forecasts, desperately needed them, for planning bombing runs and naval operations and amphibious landings, and Lorenz turned out to be good at it. Good enough that after the war, he stayed in the field, eventually ending up at MIT, where by the late 1950s he was a professor of meteorology and deeply interested in a question that had nagged weather forecasters for decades. Why are weather predictions so bad? Now, think about what weather forecasting looked like in the late 1950s and early 1960s. The dream, going all the way back to the Norwegian meteorologist Wilhelm Bjerknes at the turn of the century, was that weather prediction should be a physics problem. You know the current state of the atmosphere, temperature, pressure, humidity, wind speed at every point. And you know the laws of physics that govern how fluids move and heat transfers and moisture condenses. So in principle, you should be able to calculate the future state of the atmosphere the same way you calculate where a cannonball will land. It's just fluid dynamics. Incredibly complicated fluid dynamics, sure, with millions of variables instead of a handful, but fundamentally the same kind of deterministic calculation that Newton had given us. Laplace's demon, applied to the sky. And by Lorenz's time, people were actually trying to do this. John von Neumann, one of the great mathematical minds of the 20th century, had championed the idea of numerical weather prediction using the new electronic computers. The first real attempt was made in 1950, using the ENIAC computer at the Aberdeen Proving Ground in Maryland, one of the earliest general-purpose electronic computers in the world. A team led by Jules Charney ran a simplified set of atmospheric equations and produced a crude 24-hour forecast. It wasn't great, but it worked well enough to prove the concept. The future of weather forecasting, everyone agreed, was computation. Get faster computers, use finer grids, include more variables, and the forecasts would get better and better. It was just a matter of engineering. More data, more computing power, more accuracy. Simple. Lorenz wasn't so sure. And this is where his particular combination of skills, mathematician by training, meteorologist by profession, gave him a perspective that pure meteorologists might not have had. He'd been building his own simplified weather models on that Royal McBee computer in his office. Not full-blown atmospheric simulations. The LGP-30 was far too slow for that. It had a clock speed of something like 4,000 operations per second. Your cheapest modern calculator blows that away. But Lorenz had distilled certain atmospheric behaviors down to a set of 12 differential equations that captured, in a very stripped-down way, some of the essential dynamics of weather, convection, heat transport, that sort of thing. He'd run these equations forward in time and watch the simulated weather evolve, and he found the patterns interesting. They looked, in a qualitative way, like real weather. They never quite repeated, but they weren't purely random either. There were recognizable patterns that would almost recur, then veer off in a new direction, just like the real atmosphere. And then came the day. It was early 1961, winter, probably January or February, though the exact date isn't recorded with certainty. Lorenz had been running one of his simulations and had gotten an interesting-looking sequence. He wanted to examine a particular stretch of it more closely, maybe extend it further. But rather than rerun the entire simulation from the very beginning, which would take a long time on that slow machine, he decided to take a shortcut. He looked at the printout from the earlier run, found the values at a point partway through, and typed those numbers back in as the starting conditions for a new run. Then he went down the hall to get a cup of coffee. Here's the thing. When he came back and looked at the new printout, at first the numbers matched the old run. For a little while, the two sequences, the original and the restarted one, tracked each other closely. But then, they started to diverge. Slightly at first, then more, and then dramatically. Within the equivalent of a few simulated days, the two runs looked completely different. Different temperatures, different wind patterns, different everything, as if they were simulations of two entirely different weather systems. Now, your first instinct might be the same as Lorenz's first instinct. Something must be wrong with the computer. A vacuum tube failing, maybe, or some kind of electrical glitch. These were early computers, after all, and hardware errors were common. But Lorenz checked, and the computer was fine. So he looked more carefully at what he'd actually done, and he found the culprit. It was so small it was almost embarrassing. The computer internally stored numbers to 6 decimal places. So a value might be stored as 0.506127, but the printout, to save space on the page, only showed 3 decimal places. It would print 0.506. And when Lorenz typed the numbers back in from the printout, he entered 0.506, not 0.506127. The difference was 0.000127. Tiny. Insignificant, you'd think. In most physical calculations, rounding off in the 4th decimal place makes no practical difference whatsoever. If you're calculating the trajectory of a rocket, a difference of 1 part in 10,000 in your initial velocity barely changes where it lands. The error stays small, proportional to the original rounding. That's how well-behaved systems work. But Lorenz's weather equations weren't well-behaved. Not in that sense. That minuscule difference, less than 1 part in 5,000, had amplified exponentially, doubling and redoubling, feeding on itself through the nonlinear interactions in the equations, until it had completely overwhelmed the original signal. The tiny rounding error hadn't just nudged the forecast slightly off course. It had sent it careening into a totally different future. And this is the moment. This is when the sleeping insight finally woke up. Because Lorenz, with his mathematical training, understood immediately what this meant. And it was devastating if you were someone who believed in long-range weather prediction. It meant that even if your model of the atmosphere was perfect, every equation exactly right, every physical process faithfully captured, your forecast would still go wrong, inevitably, because you can never measure the initial conditions perfectly. There's always some uncertainty, some rounding, some limit to how precisely you can measure the temperature and pressure and humidity at every point on the globe. And in a system like the atmosphere, that uncertainty doesn't stay small. It grows, it explodes, it eats your forecast alive. Think about what that means for a second. It's not that we need better instruments, though better instruments are nice. It's not that we need faster computers, though faster computers help extend forecasts a little. The problem is fundamental. It's baked into the mathematics of the system itself. There is a hard horizon beyond which weather prediction becomes impossible in principle, not just in practice. And that horizon turns out to be somewhere around 10 to 14 days, depending on the specific atmospheric conditions. Beyond that, you're essentially guessing. Lorenz published his findings in 1963 in a paper in the Journal of the Atmospheric Sciences titled Deterministic Non-Periodic Flow. It's one of the most important scientific papers of the 20th century, and almost nobody read it. At least not at first. It was published in a meteorology journal, and the physicists and mathematicians who might have appreciated its deeper implications weren't reading meteorology journals. The paper's language was technical but understated. Lorenz wasn't one for grand pronouncements. He simply laid out the mathematics, showed the sensitivity to initial conditions, and noted the implications for prediction. The word chaos doesn't appear anywhere in the paper. That term wouldn't be coined for another 12 years. But the ideas were all there, and they were profound. Lorenz had done something remarkable. He'd taken Poincaré's abstract mathematical insight about the three-body problem and demonstrated it concretely, viscerally, in a system that everyone could relate to. Weather. The thing you experience every day. The thing the forecaster on the evening news tries to predict. And he'd shown that the unpredictability wasn't a failure of science or technology. It was a feature of the system, deterministic, but unpredictable, governed by precise laws, but fundamentally resistant to long-term forecasting. Now, here's something beautiful that came out of Lorenz's continued work on those equations. After the 1963 paper, he kept exploring, kept simplifying, trying to strip the problem down to its absolute essence. And eventually, he arrived at a system of just 3 equations, not 12, just 3, that captured the essential behavior he'd observed. 3 simple-looking differential equations with 3 variables, and when you let them run, they produce this extraordinary, endlessly complex trajectory through 3-dimensional space. The trajectory never repeats, never crosses itself. But it's not random either. It's drawn to a particular region of space and traces out this shape that looks, from certain angles, like a butterfly's wings. 2 lobes, with the trajectory spiraling around one lobe for a while, then flipping unpredictably to the other, then back, never settling into a fixed pattern. This shape came to be called the Lorenz attractor, and it became one of the iconic images of chaos theory, though Lorenz himself wouldn't see it visualized properly until computer graphics caught up years later. What makes it so remarkable is that it's a strange attractor, which is a concept that deserves its own explanation, because it reveals something deep about how chaotic systems actually behave. See, when you hear chaos, you probably think of total disorder, everything flying apart, no structure at all. But that's not what Lorenz's equations do. The trajectories are confined. They stay on the attractor. They're bounded, organized in a sense, drawn to this particular butterfly wing shape. But within that structure, the specific path is unpredictable. It's order and disorder coexisting, structure and randomness intertwined. And that combination is what makes chaos so different from both the clockwork determinism of Newton and the pure randomness of, say, radioactive decay. And the butterfly connection goes deeper than just the shape of the attractor. In 1972, Lorenz gave a talk at a meeting of the American Association for the Advancement of Science, and the title of his talk, which may or may not have been suggested by the session organizer, Philip Marelise, the historical record is a little fuzzy on this, was, "Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" That title captured the public imagination in a way that deterministic non-periodic flow never could. The butterfly effect, the idea that tiny causes can have enormous consequences. It became the most famous metaphor in all of chaos theory, maybe in all of modern science. And it's a beautiful metaphor, but it's also frequently misunderstood, so let's sit with it for a moment. Because getting it right matters. The butterfly effect does not mean that a butterfly literally causes a tornado. It's not about a specific chain of cause and effect where you can trace the flap of a wing through a sequence of air currents that build and build until a tornado forms. That's not what's happening. What Lorenz was really saying is something subtler and, honestly, more unsettling. He was saying that the atmosphere is so sensitive to its initial state that two versions of the atmosphere that differ only by the tiny puff of air from a butterfly's wing will eventually evolve into completely different weather patterns. In one version, there's a tornado in Texas next month. In the other, there isn't. But it's not that the butterfly caused the tornado. It's that the system is so exquisitely sensitive that any perturbation, no matter how small, will eventually lead to a completely different outcome. The butterfly is just a stand-in for the smallest imaginable disturbance, and the point is that you can't separate the important causes from the unimportant ones, because in a chaotic system, everything matters. Every molecule of air, every degree of temperature, every tiny fluctuation feeds into the nonlinear dynamics and gets amplified. This idea was thrilling and terrifying in equal measure, and through the 1960s and into the 1970s, it started to percolate outward from meteorology into other fields, slowly at first. But there were other people working on completely different problems who were stumbling onto the same fundamental phenomenon, this eerie sensitivity, this deterministic randomness, this order hiding inside apparent disorder. And one of the most fascinating of these parallel discoveries was happening in the world of pure mathematics, in the work of a man who was, in almost every way, the opposite of the quiet, methodical Edward Lorenz. His name was Benoit Mandelbrot, and he was working at IBM's research lab in Yorktown Heights, New York, and he was obsessed with a question that seemed, on the surface, to have nothing to do with weather or differential equations at all. He wanted to know, how long is the coast of Britain? And the answer, it turns out, is that it depends entirely on how you measure it. Think about that for a second. You'd think the coastline of Britain has a definite length, right? It's a physical thing. You could look it up in an atlas, and you'll find a number, something like 12,700 kilometers, give or take. But Mandelbrot's insight, which he published in a now famous 1967 paper called "How Long is the Coast of Britain?" statistical self-similarity and fractional dimension, was that this number is essentially arbitrary. It depends on the length of your measuring stick. Here's what he meant. Imagine you're measuring the coastline with a ruler that's 100 kilometers long. You start at one end of Britain. You lay the ruler along the coast. You mark where it ends. You pivot it to follow the next stretch, and you keep going. You'd get some total number. Let's say you lay the ruler down maybe 120 times, so you'd get about 12,000 kilometers. Fine. But now imagine you switch to a ruler that's only 50 kilometers long. With this shorter ruler, you can follow the coast more closely. You can trace into bays and around headlands that the longer ruler just skipped over. And when you add up all those 50-kilometer segments, you get a longer total, maybe 13,000 kilometers. Okay, so you switch to a 10-kilometer ruler. Now you're tracing into every little inlet, every harbor, every rocky outcropping. The total gets longer still. A 1-kilometer ruler. Longer again. A 1-meter ruler. Now you're tracing around individual boulders, following the edge of every tidal pool. The number keeps growing. And here's the thing that Mandelbrot realized. It never converges. With a normal geometric shape, like a circle, if you measure its circumference with finer and finer rulers, your answer gets closer and closer to a single true value. It converges. The coastline of Britain doesn't do that. The finer your measurement, the longer it gets, and there's no natural stopping point. In principle, if you could measure around every grain of sand, every molecule, the length would be astronomical. The coastline of Britain is, in a very real mathematical sense, infinite. Now, this wasn't entirely new as a mathematical observation. A Swedish mathematician named Helge von Koch had described something similar back in 1904 with what we now call the Koch snowflake, a shape you build by starting with an equilateral triangle, then adding a smaller triangle to the middle of each side, then adding even smaller triangles to each of those new sides, and so on forever. The resulting shape has a finite area. You could draw a circle around it. But its perimeter is infinite. It just keeps getting longer and longer as you add detail at every scale. And what's remarkable about it is that it looks the same no matter how much you zoom in. Every tiny section of the boundary, when magnified, looks just like the whole thing. This property, looking the same at every scale, is called self-similarity. But here's what Mandelbrot did that was different from Koch and from the other mathematicians who had played with these kinds of shapes. They had treated them as curiosities, as pathological exceptions, as monsters that lived in the margins of mathematics. Mandelbrot looked at the real world and said, "No, these aren't monsters. These are everywhere. The coastline of Britain is like this. The branching pattern of a tree is like this. The way a river network spreads across a landscape is like this. The shape of a cloud, the surface of a mountain, the pattern of blood vessels in your lungs, all of these things have this property of being rough and detailed at every scale, of looking similar whether you zoom in or zoom out." And Mandelbrot gave them a name. He called them fractals, from the Latin word fractus, meaning broken or fragmented. And he argued that they needed a new kind of geometry to describe them, not the smooth, clean geometry of Euclid, with its perfect circles and straight lines, but a rougher, wilder geometry that could capture the actual texture of the natural world. Now, let's talk about Mandelbrot himself for a moment, because his life story is inseparable from his ideas. He was born in Warsaw, Poland, in 1924, into a Lithuanian Jewish family. When he was 11, his family moved to Paris, sensing what was coming in Europe. When the war arrived, the family fled south, and young Benoit spent much of the occupation hiding in the French countryside, missing years of formal schooling. He later said that this irregular education was actually a gift. He never learned mathematics in the orderly, step-by-step way that most students do. Instead, he developed an intensely visual, geometric intuition. He could see shapes and patterns where other mathematicians saw only equations. He thought in pictures. After the war, he studied at the École Polytechnique in Paris, then at Caltech, then back in France, and he bounced around between institutions and disciplines in a way that was unusual and, frankly, career-limiting in the academic world of the 1950s and 60s. He didn't fit neatly into any department. He wasn't quite a pure mathematician, wasn't quite a physicist, wasn't quite an economist, though he worked in all these fields. This is part of why he ended up at IBM's research lab in Yorktown Heights. IBM, at the time, was one of the few places that would hire brilliant misfits and just let them think. They didn't care what department you belonged to. They cared about ideas, and Mandelbrot had a lot of ideas. Before he got to coastlines, he'd been looking at something completely unexpected: cotton prices. In the early 1960s, an economist named Hendrik Houthakker at Harvard had a dataset of cotton prices going back decades, and the price fluctuations didn't behave the way economic theory said they should. Standard models assumed that price changes followed a normal distribution, a bell curve, where small changes are common and big changes are rare. But the cotton price data had too many big swings, way too many. The tails of the distribution were fat, meaning that extreme events, crashes, spikes, happened far more often than a bell curve would predict. Mandelbrot looked at this data and noticed something strange and beautiful. The pattern of price fluctuations looked the same whether you zoomed in to look at daily changes, weekly changes, or monthly changes. There was that self-similarity again. The statistical texture was the same at every timescale. And he realized that this wasn't a bell curve at all. It was something wilder, something with what mathematicians call a power law distribution, where extreme events are rare, but not nearly as rare as you'd expect. He published this work in 1963, the same year Lorenz published his paper on deterministic non-periodic flow. 2 papers, same year, both pointing at the same deep truth from completely different directions, that the systems we live with, whether they're weather systems or financial markets, have a kind of built-in wildness that our standard mathematical tools just aren't equipped to handle. So why does this matter for chaos theory? Because fractals turned out to be the geometry of chaos. Remember the Lorenz attractor, that butterfly-shaped figure that Lorenz's weather equations traced out in 3-dimensional space? That shape is a fractal. It's not a simple surface. If you zoom in on it, you find that what looks like a single sheet is actually made up of infinitely many layers, pressed infinitely close together, but never quite touching. It has a dimension that isn't a whole number. It's not 2-dimensional like a sheet of paper, and it's not 3-dimensional like a solid block. It's somewhere in between. About 2.06 if you want to get specific. And this fractional dimension, this is where the word fractal really earns its name, is a signature of chaotic systems. Let me try to make that idea of fractional dimension more intuitive, because it's one of those concepts that sounds impossible until it clicks. Think about a ball of yarn. From far away, it looks like a solid sphere, a 3-dimensional object. But get closer, and you see it's made of a single long thread, a 1-dimensional object. So what dimension is a ball of yarn? It depends on the scale you're looking at. At one scale, it's 3-dimensional. At another, it's 1-dimensional. Mandelbrot's genius was to say, Some objects genuinely live between dimensions, and we need a number system that can express that. A coastline is more than a one-dimensional line because it's so crinkly and convoluted that it starts to fill up area, but it's less than a two-dimensional surface. So maybe it's something like 1.25 dimensions. The coast of Britain, as it happens, has a fractal dimension of about 1.25. The more jagged and complex a coastline, the higher its fractal dimension. Norway's coast, with all those fjords cutting deep inland, has a fractal dimension closer to 1.52. And this isn't just a neat mathematical trick. It's a genuine measurement of complexity, of roughness, of how thoroughly a shape fills the space it lives in. And when you start looking for fractals in nature, you find them absolutely everywhere. The branching pattern of your lungs, where the trachea splits into bronchi, which split into bronchioles, which split into smaller and smaller passages, is fractal. And there's a beautiful reason for that. Your lungs need to pack an enormous surface area into a small volume so that oxygen can diffuse efficiently into your blood. The total internal surface area of a human lung, if you could spread it all out flat, is something like 50 to 75 square meters, roughly the size of half a tennis court, folded up inside your chest. Fractal branching is how nature solves the problem of maximizing surface area within a confined space. The same principle shows up in trees, which need to collect as much sunlight as possible, and in river networks, which need to drain water from as much land area as possible, and in the circulatory system, which needs to deliver blood to every cell in your body. Fractals aren't just mathematical abstractions. They're engineering solutions that evolution discovered long before any human mathematician wrote them down. But Mandelbrot's work also connected to chaos theory in a more specific, more technical way, and this is where things start to get really deep. When you have a chaotic system, like Lorenz's weather equations, and you look at its strange attractor, the fractal structure of that attractor tells you something profound about the dynamics. It tells you that the system is stretching and folding phase space over and over, like a baker kneading dough. Imagine you take a lump of dough, stretch it out, fold it over, stretch it again, fold it again. If you put a drop of food coloring in the dough and then did this 100 times, that drop would be smeared out into an incredibly thin, incredibly long ribbon that winds through the entire lump. 2 points that started right next to each other in the dough would end up far apart, but 2 points that started far apart might end up close together. This stretching and folding is exactly what happens in the phase space of a chaotic system, and it's why nearby initial conditions diverge. The stretching pulls them apart, and why the attractor has that infinitely layered fractal structure. The folding keeps pressing the layers back together. This image of stretching and folding is maybe the single most useful mental model for understanding chaos. It captures both the sensitivity, the divergence of nearby trajectories, and the boundedness. The fact that the system doesn't fly off to infinity, but stays confined to a finite region of phase space. And it explains why prediction becomes impossible after a certain time horizon. Every fold doubles the number of layers, and every stretch doubles the separation between nearby points. After enough iterations, you'd need to know the initial position of your food coloring drop with infinite precision to predict where it ends up. Any uncertainty, no matter how small, gets amplified exponentially. Now, through the 1970s, these ideas, Lorenz's sensitivity, Mandelbrot's fractals, the strange attractors that lived in between, were still scattered across different fields. Meteorologists knew about Lorenz. Mathematicians knew about some of these fractal structures. Physicists were starting to notice strange behavior in their own experiments. But there wasn't yet a unified sense that all of these things were part of the same story. That synthesis was coming, though, and one of the key figures who helped bring it together was a physicist named Mitchell Feigenbaum, who was working at Los Alamos National Laboratory in the mid-1970s, and who discovered something so unexpected, so eerily universal, that when he first showed his results to other physicists, most of them simply didn't believe him. What Feigenbaum found was a number, a single, precise constant that kept showing up in system after system after system, in places where it had absolutely no business showing up. And to understand what that number means, we need to talk about a particular route that many systems take on their way from orderly behavior into chaos, a route called period doubling. So let's set the stage. Feigenbaum was, by most accounts, a brilliant but somewhat restless physicist. He'd done his PhD at MIT, worked on particle physics, but by the mid-1970s, he drifted toward the kinds of problems that didn't fit neatly into any one department. He ended up at Los Alamos, which was a fascinating place to be at that time. It still had that legacy of the Manhattan Project, this culture of bringing together people from wildly different disciplines and letting them think about hard problems. And Feigenbaum was thinking about a deceptively simple question. He was playing around with something called the logistic map, which is one of the simplest mathematical systems you can possibly write down. It's a single equation, one line, and yet it contains, within that one line, an entire universe of complex behavior. Here's how the logistic map works. You take a number between 0 and 1, call it x. Then you apply a rule. You multiply x by 1 minus x, and then multiply the whole thing by some constant, which we'll call r. That gives you a new number, which becomes your next x, and you just keep doing that over and over. Feed the output back in as the new input. That's it. That's the whole system. One number goes in, one number comes out, and you repeat. Now, what makes this interesting is what happens as you change that constant r. When r is small, say around 2, the system is boring. You start with any value of x, and after a few iterations, it settles down to a single fixed number and just stays there. Completely predictable, completely stable, like a ball rolling to the bottom of a bowl and stopping. But when you increase r a little, push it up past 3, something happens. The system stops settling to a single value. Instead, it starts alternating between two values. It bounces back and forth, high, low, forever. Mathematicians call this a period 2 cycle. The system has doubled its period. Instead of repeating every one step, it repeats every 2 steps. Okay, that's mildly interesting. But here's where it gets good. You keep increasing r, and at some higher value, the period 2 cycle becomes unstable, and the system starts cycling between 4 values. Period 4. Then you increase r a bit more, and it goes to period 8, then 16, then 32. Each time, the period doubles. And here's the thing that Feigenbaum noticed. The amount you have to increase IR to get the next doubling gets smaller and smaller each time. The doublings come faster and faster, closer and closer together, until they're piling up on top of each other in a kind of cascade. And then, at a very specific critical value of R, around 3.56995, the period has doubled infinitely many times, and the system crosses over into chaos. Full-blown, aperiodic, sensitive to initial conditions chaos. From a one-line equation. That cascade, that staircase of period doublings accelerating toward chaos, is called the period doubling route to chaos. And it's beautiful in a way that's hard to overstate. Because it means chaos doesn't just arrive out of nowhere. It has a pathway. There's a structured, orderly transition from simple behavior to complex behavior, and that transition follows precise mathematical rules. Now, what Feigenbaum did, and this is the part that stunned everyone, was measure the rate at which those doublings accelerate. He looked at the intervals between successive doublings. How far apart are they? And he found that each interval is shorter than the previous one by a very specific ratio. If you take the width of one interval and divide it by the width of the next, you get a number. And that number, as you go further and further into the cascade, converges to a constant, approximately 4.669201,609. That's Feigenbaum's constant, and it's sometimes written with the Greek letter delta. Now, you might think, okay, that's a neat mathematical curiosity about one particular equation. But here's what's wild. Feigenbaum tried a different equation, a completely different mathematical function, and ran through the same analysis, different formula, different shape, different everything, and he got the same constant, 4.669. He tried another one, same constant, another, same. He kept going, trying equation after equation, and the number kept coming back, like a signal buried in static that you suddenly can't stop hearing. 4.669201609. This was, to put it mildly, not expected. Different equations describe different physical systems. They have different mathematical properties, different shapes, different behaviors. There's no obvious reason they should share anything in common when it comes to how they transition into chaos. And yet, here was this number, this constant, showing up everywhere, like a fingerprint that nature keeps leaving at every crime scene. Feigenbaum spent months checking and rechecking his results. He was working on a handheld HP 65 calculator at first. This was the mid-1970s, and even at Los Alamos, computer time wasn't always easy to come by. He'd stay up late at night, running these iterations by hand, stacking up the numbers, and every time 4.669 would emerge from the data like a ghost. He eventually proved mathematically that the constant was universal, meaning it applies to any smooth, single-humped function undergoing period doubling. It doesn't matter what the equation is. If the function has a single maximum, one hump, and you tune a parameter to drive it through period doubling, the ratio of successive bifurcation intervals will converge to Feigenbaum's constant, always. Think about what that means for a second. It means there's a deep structural similarity between all these different systems, a kind of hidden symmetry in the way order breaks down into chaos. The specific details of the system don't matter. What matters is the shape of the transition, and that shape is universal. When Feigenbaum first tried to publish his results, around 1975 and 1976, he had trouble. The paper was rejected. Reviewers didn't know what to make of it. It didn't fit into any established category. It wasn't quite physics, wasn't quite pure mathematics, wasn't quite dynamical systems theory in any traditional sense. Some people thought it was trivially obvious. Others thought it was probably wrong. A few thought it was interesting but couldn't see why it mattered. This is a pattern you see over and over in the history of chaos theory. People making genuinely profound discoveries and then struggling to get anyone to pay attention because the discovery doesn't fit into the existing intellectual boxes. But gradually, word spread. Other researchers started checking Feigenbaum's results and confirming them. And then something really remarkable happened. Experimentalists started finding the constant in real physical systems, not just in equations on a page, but in actual, physical, measurable phenomena. One of the first confirmations came from experiments on fluid convection, basically heating a fluid from below and watching the flow patterns. As you increase the temperature difference, the flow goes through a series of transitions. First, it's steady. Then it develops a periodic oscillation. Then the oscillation doubles in frequency. Then it doubles again. And the ratios between those doublings, 4.669. Right there in the laboratory, in real swirling fluid, Feigenbaum's constant showed up like it had been waiting to be found. It was also found in electronic circuits driven to oscillation, in certain chemical reactions, in the behavior of laser systems, even in dripping faucets. There was a famous experiment where researchers carefully controlled the drip rate of a faucet and found period doubling on the route to chaotic dripping, and the Feigenbaum constant was there, governing the spacing of the transitions, a dripping faucet and a convecting fluid, and a mathematical equation, all sharing the same deep constant. That's the kind of universality that makes physicists sit up very straight in their chairs. And there's actually a second Feigenbaum constant, usually called alpha, which is approximately 2.5029. This one describes how the spacing of the values within each cycle scales from one doubling to the next. Together, these two constants completely characterize the geometry of the period doubling cascade. They're as fundamental to chaos theory as pi is to circles or e is to exponential growth. They're not derived from any particular physical law. They emerge from the mathematics of iteration itself, from what happens when you feed outputs back into inputs over and over and tune a parameter toward the edge of chaos. This idea of universality was transformative. Before Feigenbaum, each chaotic system seemed like its own special case. Lorenz had his weather model. Fluid dynamicists had their turbulence. Ecologists had population models that behaved erratically. But there wasn't a sense that these were all manifestations of the same underlying mathematics. Feigenbaum's constant was one of the first pieces of hard evidence that chaos wasn't just a collection of curiosities. It was a genuine field, with universal laws, with constants of nature that transcended any particular application. It gave chaos theory the kind of mathematical backbone that made serious physicists and mathematicians willing to invest their careers in it. And the timing was perfect, because by the late 1970s and early 1980s, something else was happening that would accelerate the whole field enormously. Computers were getting powerful enough and accessible enough that researchers could actually visualize what these systems were doing. You could iterate an equation 1,000,000 times and plot the results. You could see the period doubling cascade unfold on a screen. You could zoom into a strange attractor and watch its fractal structure reveal itself at finer and finer scales. And one of the most stunning objects that emerged from this computational exploration was something we've already brushed against, the Mandelbrot set, which Benoit Mandelbrot himself began investigating in earnest around 1979 and 1980, using the computers at IBM. But the Mandelbrot set wasn't just a pretty picture. It was a map, a kind of atlas of dynamical behavior, and buried within its infinitely complex boundary was every period doubling cascade Feigenbaum had ever studied, along with structures and transitions that nobody had even begun to name yet. And that's what makes it one of the most remarkable objects in all of mathematics. It's not just complex, it's a kind of encyclopedia of complexity itself. So let's talk about what the Mandelbrot set actually is, because the equation behind it is almost absurdly simple. You take a number, and we're working with complex numbers here, which just means numbers that have two parts, a real part and an imaginary part. So you can think of them as points on a flat plane, and you apply a rule. You take the number, square it, and add a constant. That's it. That's the whole operation. Z goes to z squared plus c, where c is some fixed complex number you've chosen. You start with z equal to 0, and you just keep doing it. Square the result, add c. Square that result, add c again. over and over. Now here's the question. The Mandelbrot set asks, for a given value of C, does this process stay bounded? Does Z stay close to the origin, never spiraling off to infinity? Or does it escape, growing larger and larger without limit? That's the only question. Stay or go. Bounded or unbounded. And the Mandelbrot set is simply the collection of all values of C for which the sequence stays bounded. You color those points black, you color everything else based on how quickly it escapes, and you get, well, you get one of the most famous images in the history of science. The shape itself is strange and beautiful. There's a main cardioid, a heart-shaped bulge, with a large circular disc attached to its left, and then smaller bulbs sprouting off in every direction, connected by thin filaments, with antennae-like tendrils reaching into the surrounding plane. And the boundary of this shape, the edge between the points that stay bounded and the points that escape, is where all the magic lives. Because that boundary is infinitely complex. You can zoom into it, and you find spirals and seahorse tails and miniature copies of the whole Mandelbrot set sitting inside itself, surrounded by their own intricate decorations, and those miniature copies have their own miniature copies, and it just never ends. The boundary has a fractal dimension. It's not a smooth curve. It's infinitely crinkly, infinitely detailed at every scale. But here's what connects this to everything we've been talking about. Each point in the Mandelbrot set corresponds to a particular dynamical system, a particular version of that Z squared plus C iteration. And the location of that point tells you what kind of behavior that system exhibits. Points deep inside the main cardioid correspond to systems that settle down to a single fixed point. They're stable and boring, dynamically speaking. Points inside that big circular disk to the left correspond to systems that oscillate between two values, period 2. And as you move along the boundary, you find regions corresponding to period 3, period 4, period 5, every possible period. And between those regions, you find the period doubling cascades that Feigenbaum discovered. You can literally trace the route to chaos along the real axis of the Mandelbrot set, watching the bifurcations happen exactly where Feigenbaum's constant predicts they should. Think about what that means. The Mandelbrot set is a single image that contains within it a complete catalog of how simple iterative systems can behave. Stability, oscillation, period doubling, chaos. It's all there, encoded in the geometry of this one shape. And Feigenbaum's universality is visible in it, because the spacing of those bifurcation points converges at exactly the ratio of 4.669, just as it does in the logistic map, just as it does in every smooth, single-humped system. The Mandelbrot set doesn't just illustrate chaos theory. In a very real sense, it is chaos theory, compressed into a geometric object. Mandelbrot himself was captivated by this, and he spent years exploring its structure, publishing papers on its properties, and, characteristically, making sure the world saw the pictures. Because Mandelbrot understood something that many pure mathematicians were slow to appreciate. Visualization wasn't just a nice bonus, it was a tool for discovery. You could see things in these computer-generated images that you'd never find through algebra alone. Patterns, symmetries, unexpected connections. They jumped out at you when you could see them. And the Mandelbrot set was the ultimate example of this. Its structure was so rich, so layered, that mathematicians are still cataloging its features today, decades later. Now, around this same period, the early to mid-1980s, chaos theory was experiencing something like a phase transition of its own. It was going from a scattered collection of results, known mainly to specialists, to a genuine intellectual movement. And a big part of that shift happened because of a group of young scientists who found each other at a place you might not expect, the University of California, Santa Cruz. This is a great story, actually. Santa Cruz in the late 1970s was not exactly a powerhouse of physics. It was a relatively new campus, kind of countercultural, nestled in the redwoods above Monterey Bay. But a small group of graduate students there, people like Rob Shaw, Doyne Farmer, Norman Packard, and James Crutchfield, became obsessed with chaos. They called themselves the Dynamical Systems Collective, though informally they were sometimes known as the Chaos Cabal. And they were doing something unusual for the time. They were approaching chaos not just as a mathematical curiosity, but as an experimental science. They built physical systems, dripping faucets, water wheel contraptions, and measured the chaotic behavior directly, comparing it to the theoretical predictions. The dripping faucet, by the way, is a wonderful example of chaos hiding in plain sight. You've experienced this. You turn a faucet almost off, and it drips at a steady rate. Drip, 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 perfectly regular. But if you open it just a tiny bit more, the dripping becomes irregular. Not random exactly, but unpredictable. Sometimes 2 quick drips followed by a pause, then 3 quick ones, then a long gap. Rob Shaw actually measured the intervals between drops with high precision and showed that the pattern of dripping undergoes a period-doubling route to chaos, just like the logistic map, just like Lorenz's convection model. Feigenbaum's constant showed up in a kitchen faucet. That's universality in action, and it's the kind of result that makes you look at the world a little differently. The Santa Cruz group was also deeply interested in a question that would become central to the field. Can you reconstruct the dynamics of a chaotic system from a single measurement? This sounds abstract, but think about what it means practically. Say you're studying the weather, and all you have is a single time series, temperature readings at one location, hour by hour. The weather system has thousands of variables: pressure, humidity, wind speed at every point in the atmosphere. But you only have this one stream of numbers. Can you somehow unfold that one-dimensional signal and reconstruct the higher dimensional attractor that the system is moving on? It turns out you can, and the technique for doing it is called delay embedding, or sometimes Takens embedding, after the Dutch mathematician Floris Takens, who proved the theoretical foundations in 1981. The idea is beautifully simple. You take your single time series, let's call the measurements x at time 1, x at time 2, x at time 3, and so on, and you create new vectors by grouping consecutive measurements together. So one point in your reconstructed space might be the triple of x at time 1, x at time 2, and x at time 3. The next point is x at time 2, x at time 3, x at time 4, and so on. You're essentially using time delays to create extra dimensions, and Takens proved that if you use enough delays, the shape you get in this reconstructed space is topologically equivalent to the true attractor of the system. It preserves all the essential geometric and dynamical properties: the stretching, the folding, the fractal structure. This was enormous for practical applications because real-world systems rarely give you the luxury of measuring every variable. You get what you get: a voltage signal from a sensor, a temperature reading, a stock price, and delay embedding gives you a principled way to extract the hidden dynamics from that limited data. The Santa Cruz group was among the first to actually apply this technique to experimental data, and their work helped bridge the gap between the beautiful mathematics of chaos and the messy reality of laboratory measurements. And this brings us to something important about chaos theory's trajectory in the 1980s: the growing tension between its theoretical elegance and its practical limitations. Because as the field matured, as more and more people got excited about it, a crucial question kept surfacing. If chaotic systems are deterministic but unpredictable, is there anything useful you can actually do with chaos theory? Or is it just telling you that prediction is impossible and you should give up? The answer turned out to be more nuanced and more interesting than either extreme. Yes, long-term prediction of chaotic systems is fundamentally limited. Lorenz had established that clearly. But short-term prediction can be dramatically improved if you understand the chaotic dynamics. And there are things you can extract from chaotic systems that don't require prediction at all. Statistical properties, geometric features of the attractor, measures of how chaotic the system is. One of the most important of these measures has a name you might have encountered: the Lyapunov exponent, named after the Russian mathematician Alexander Lyapunov, who worked on stability theory back in the 1890s, long before anyone was thinking about chaos in the modern sense. The Lyapunov exponent quantifies exactly how sensitive a system is to initial conditions. Remember Lorenz's discovery: two weather simulations starting from nearly identical conditions diverging exponentially over time? The Lyapunov exponent is the number that tells you the rate of that exponential divergence. If it's positive, nearby trajectories separate exponentially fast, and you have chaos. If it's zero or negative, you don't. And the size of the exponent tells you how quickly prediction becomes useless. A larger Lyapunov exponent means a shorter prediction horizon. Here's a nice way to think about it. Imagine you know the initial state of a system to some precision. Say, you've measured everything to 6 decimal places. A positive Lyapunov exponent means that your uncertainty grows exponentially with time. Each tick of the clock, the uncertainty multiplies by some factor. Eventually, your 6 decimal places of precision have been eaten up, and you know nothing. The Lyapunov exponent tells you how fast those decimal places get consumed. For Lorenz's weather model, the prediction horizon was about 2 weeks for the solar system, and this is something that would become clear in the late 1980s and 1990s. The Lyapunov time for the orbits of the inner planets is somewhere around 5 million years, which sounds like a long time until you remember that the solar system is 4.5 billion years old, meaning that the detailed positions of the planets are genuinely chaotic over geological timescales. We can predict where Mars will be next year with exquisite precision, but we literally cannot know where it was 1 billion years ago, not because we lack data, but because the dynamics themselves amplify any uncertainty beyond recovery. And this idea that chaos imposes fundamental limits on knowledge, not just practical ones, was philosophically jarring for a lot of people. It wasn't like quantum mechanics, where uncertainty comes from the inherent randomness of measurements at the subatomic scale. Chaos is fully deterministic. The equations are exact. There's no randomness anywhere in the system, and yet prediction fails, inevitably and irreversibly, because information about initial conditions is destroyed by the dynamics themselves. It's a different kind of unknowability, and in some ways a more unsettling one, because you can see the equations, you can write them down, they're perfectly well defined, and they still won't tell you what happens next, not if you wait long enough. This philosophical dimension of chaos theory attracted attention far beyond physics and mathematics, and by the mid-1980s, the field was gaining a kind of cultural momentum that few scientific disciplines ever achieve. And a lot of that momentum crystallized around a particular question: that had been simmering since Lorenz's earliest work. The relationship between chaos and turbulence. That ancient, unsolved problem of fluid dynamics that had frustrated physicists for over a century. Because turbulence, the wild, swirling, apparently random motion of fluids at high speeds, had always seemed like it might be fundamentally random, fundamentally intractable. But chaos theory was suggesting something different, that maybe turbulence wasn't random at all, that maybe it was deterministic chaos operating in a very high-dimensional space, and that maybe, just maybe, the tools being developed to analyze strange attractors and Lyapunov exponents and fractal dimensions could finally crack open the problem that had defeated everyone from Leonardo da Vinci to Werner Heisenberg. And that's not an exaggeration, by the way. Heisenberg, near the end of his life, reportedly said something to the effect of, "When I meet God, I'm going to ask him two questions: why relativity and why turbulence? And I really believe he'll have an answer for the first." Whether or not he actually said exactly that, the sentiment captures just how deeply turbulence had frustrated the greatest minds in physics. It was the problem that wouldn't yield. So let's talk about what turbulence actually is, because it's one of those things you've experienced 1,000 times but maybe never really thought about in mechanical terms. You're sitting on an airplane, cruising smoothly, and then suddenly the plane starts shaking. That's turbulence, obviously. But turbulence isn't just bumpy air. It's a specific kind of fluid behavior where smooth, orderly flow, what physicists call laminar flow, breaks down into something chaotic, full of eddies and vortices at every scale, swirling structures that form and dissolve and interact in ways that seem completely unpredictable. You can see it when you watch smoke rise from a candle. For the first inch or two, the smoke rises in a smooth, elegant column. Then, at some point, it just falls apart. It starts curling, folding, breaking into wisps and whirls that tumble over each other. That transition, from smooth to wild, is the onset of turbulence, and understanding exactly why and how it happens has been one of the deepest open problems in all of classical physics. The equations that govern fluid flow have been known since the 1840s. They're called the Navier-Stokes equations, named after Claude Louis Navier and George Gabriel Stokes, and they're basically Newton's second law applied to fluids. Force equals mass times acceleration, but written for a continuous flowing substance instead of a single particle. And here's what's maddening about them. The equations are well established. They're based on solid physics. And for simple laminar flows, they give beautiful, exact solutions. But for turbulent flows, they become essentially unsolvable in any closed form. The nonlinear terms in the equations, and there's that word again, nonlinear, the same ingredient that gives you chaos. Those nonlinear terms create such mathematical complexity that nobody has ever proven whether smooth solutions always exist for the three-dimensional Navier-Stokes equations. In fact, that question is one of the 7 Millennium Prize problems in mathematics. There's a $1 million bounty on it, and it remains unclaimed. So when chaos theory came along and said, look, deterministic systems with nonlinear dynamics can produce behavior that looks random but actually has hidden structure, that strange attractors have finite fractal dimensions even when the motion looks infinitely complex. You can imagine how exciting that was for people studying turbulence. Because the traditional view, going back to the Russian mathematician Andrei Kolmogorov's work in 1941, treated turbulence statistically. Kolmogorov described turbulence as a cascade of energy from large eddies down to smaller and smaller ones, and his statistical theory was remarkably successful at predicting certain averaged properties. But it didn't tell you what was actually happening in the flow at any given moment. It was like describing a crowd by its average height without knowing where any individual person was standing. Chaos theory offered a different lens. In 1971, even before Lorenz's work had fully penetrated the physics community, the Belgian physicist David Ruel and the Dutch mathematician Floris Takens, the same Takens who later gave us the embedding theorem, published a paper proposing something radical. They suggested that turbulence wasn't the result of an infinite number of independent oscillations all piling on top of each other, which was the prevailing idea going back to Lev Landau's 1944 theory. Instead, Ruel and Takens argued that turbulence could arise from just a small number of interacting modes, as few as 3 or 4, that through their nonlinear coupling would produce a strange attractor. They were saying that the apparent infinite complexity of turbulence might actually live on a relatively low-dimensional geometric object in phase space. This was a genuinely bold claim, and it was controversial. A lot of fluid dynamicists were skeptical. Turbulence looks so complicated, so wildly disordered, that the idea of it being governed by a low-dimensional attractor seemed almost too good to be true. And in a sense, the skeptics had a point. Fully developed turbulence in three-dimensional flows does appear to involve very high-dimensional dynamics, possibly hundreds or thousands of active degrees of freedom. The Ruel-Takens picture works best for the onset of turbulence, those early stages where laminar flow first begins to break down, and experiments in the late 1970s and early 1980s did find evidence of strange attractors in certain carefully controlled fluid systems. Harry Swinney and Jerry Golub, working at the University of Texas and Haverford College respectively, did beautiful experiments with a fluid held between 2 rotating cylinders, a setup called Quette-Taylor flow, and they found that the transition to turbulence followed the Ruel-Takens scenario rather than the Landau picture. The flow went through a small number of bifurcations and then jumped to a strange attractor, just as predicted. It was one of the first experimental confirmations that chaos theory had something real to say about fluid dynamics. But here's the honest truth about turbulence and chaos, and it's worth sitting with for a moment. Chaos theory illuminated the onset of turbulence beautifully. It explained how orderly flow could become disordered through a small number of steps. But fully developed turbulence, the roaring, multi-scale, energy-cascading maelstrom you get in a jet engine exhaust or a thunderstorm or ocean currents, that remains only partially understood through the lens of low-dimensional chaos. The attractor dimensions are too high, the dynamics too complex, for the elegant tools that worked so well on Lorenz's 3 equations or Feigenbaum's one-dimensional maps. Turbulence, in a way, humbled chaos theory, even as chaos theory shed new light on it. And that's okay. That's how science works. You don't solve everything, but you change the way people think about the problem, and that shift in thinking opens doors that were previously invisible. And speaking of opening doors, this is a good moment to talk about where chaos theory went beyond the physical sciences, because one of the most remarkable things about the field in the 1980s and 1990s was how it spread into disciplines that had never had much use for differential equations or phase space diagrams. Biology, for instance. The human heart, it turns out, is a spectacular example of a dynamical system that lives on the edge between order and chaos, and understanding that edge has genuinely saved lives. Think about your heartbeat for a second. You probably imagine it as a steady, metronomic rhythm. Lub-dub, lub-dub, perfectly regular. But if you actually measure the time intervals between successive heartbeats with enough precision, you discover something surprising. A healthy heart is not perfectly regular. The intervals fluctuate, subtly but measurably, in a pattern that has fractal characteristics. Your heart rate variability, as it's called, shows correlations across multiple timescales, beat to beat, minute to minute, hour to hour, in a way that resembles a fractal time series. And here's what's really interesting. A heartbeat that becomes too regular, too rigidly periodic, is actually a warning sign. It can indicate that the heart's regulatory systems are losing their flexibility, their ability to adapt to changing demands. Paradoxically, a little bit of chaos, a little bit of that sensitive, complex fractal variability is a sign of health. Arie Goldberger, a cardiologist at Harvard, was one of the pioneers of this idea in the 1980s and 1990s. He and his colleagues showed that the loss of fractal heart rate variability was associated with aging and with various forms of heart disease. The healthy heart, in their framework, operates in a regime that's neither perfectly periodic nor fully random, but somewhere in between, at the edge of chaos, as some researchers like to say, and on the dangerous end of the spectrum, when the heart's electrical system tips into true chaos, when the orderly waves of electrical activation that coordinate the heart muscle break down into disordered, self-sustaining spiral waves. You get ventricular fibrillation, which is cardiac arrest. The heart quivers instead of pumping. Without intervention, you die within minutes. So chaos in the heart is a double-edged sword. A little variability is healthy, but too much disorder is lethal. Understanding the dynamics of that transition, from healthy complexity to fatal chaos, has informed the design of implantable defibrillators and the development of drugs that stabilize cardiac rhythms. And the heart is just one example. Chaos theory found applications in ecology, where population models like the logistic map, remember that equation, the simple one that Feigenbaum studied, where you just square a number and add a constant, turned out to describe real population dynamics in certain insect species. Robert May, an Australian physicist turned ecologist who later became president of the Royal Society, published a landmark paper in 1976 called Simple Mathematical Models with Very Complicated Dynamics, and it was essentially a tutorial on the logistic map aimed at biologists. May argued that ecologists needed to understand that even the simplest population models could produce wildly unpredictable behavior, and that apparent randomness in population data didn't necessarily mean the environment was random. It might mean the underlying dynamics were chaotic. This was a genuinely important insight, because it changed how ecologists thought about fluctuating populations. Before May's paper, if a population of, say, spruce budworms oscillated wildly from year to year, the default assumption was that some external factor, weather, predators, disease, was driving the fluctuations. May showed that the fluctuations could be intrinsic, generated by the population's own growth dynamics, even in a perfectly constant environment. Neuroscience picked up the thread too. The brain, after all, is the most complex dynamical system we know of. Roughly 86 billion neurons, each connected to thousands of others, firing in patterns that somehow give rise to thought, perception, memory, consciousness. Walter Freeman, a neurophysiologist at UC Berkeley, was one of the earliest advocates for applying chaos theory to brain dynamics. Starting in the 1980s, Freeman studied the olfactory system, the part of the brain that processes smell. and found evidence that the collective electrical activity of olfactory neurons exhibited chaotic dynamics. He argued that chaos was actually functional in the brain, that it allowed the neural system to remain in a state of readiness, poised to rapidly shift between different patterns of activity in response to different stimuli. A brain stuck in a fixed pattern would be rigid, unable to adapt. A brain in full chaos would be noise, unable to sustain coherent thought. But a brain operating near the edge of chaos could balance stability with flexibility, and Freeman believed that was exactly what he was seeing in his data. Now, it's worth being honest here. The application of chaos theory to biology and neuroscience has been more suggestive than definitive in many cases. Biological systems are noisy, high-dimensional, and hard to measure with the precision you'd need to rigorously establish the presence of low-dimensional strange attractors. Some of the early enthusiasm for finding chaos everywhere, in EEG signals, in epidemiological data, in stock markets, turned out to be premature. People applied the tools of chaos theory, like correlation dimension estimates and Lyapunov exponent calculations, to data sets that were too short, too noisy, or too poorly understood to support strong conclusions. There was a period in the late 1980s and early 1990s where chaos became almost a buzzword, applied loosely and sometimes carelessly to anything that looked complicated. And the inevitable backlash came. Papers showing that many claimed detections of chaos in real-world data didn't hold up under more rigorous analysis. But that correction, that tightening of standards, was itself a healthy part of the field's maturation, and the core insights survived the hype cycle intact. Deterministic systems can produce behavior that is practically indistinguishable from randomness. Sensitivity to initial conditions imposes fundamental limits on prediction. Strange attractors provide geometric structure within apparent disorder. Universality means that the same patterns, period doubling, the same constants, the same bifurcation sequences appear across wildly different systems. These ideas didn't go away when the hype faded. They became part of the permanent intellectual infrastructure of science. And perhaps the place where chaos theory's mature legacy is most visible today, where it quietly shapes something that affects your life every single day without you ever thinking about it, is in weather forecasting. Because remember Lorenz, back in his office at MIT in 1961, discovering that his weather model was exquisitely sensitive to tiny differences in starting conditions? That discovery didn't just become a famous anecdote about butterflies and storms. It fundamentally changed how the entire enterprise of weather prediction works. And the story of how that happened, how meteorologists took Lorenz's unsettling discovery and turned it into something genuinely useful, is one of the most quietly brilliant chapters in the history of applied science. So let's think about what weather forecasting looked like before chaos theory really sank in. For most of the 20th century, the basic approach was what you'd call deterministic forecasting. You take the best measurements you can get of the current state of the atmosphere, temperature, pressure, humidity, wind speed, and direction at thousands of locations and many altitudes, and you feed all of that into a numerical model, a massive system of equations based on fluid dynamics and thermodynamics. The computer crunches through those equations, stepping forward in time, and out comes a prediction. One prediction. A single forecast. Tuesday will be sunny with a high of 72. Rain expected Thursday afternoon. And for short-range forecasts, this worked remarkably well. As computers got faster and models got more sophisticated through the 1960s, 70s, and 80s, weather prediction improved steadily. A 3-day forecast in the 1980s was about as accurate as a 1-day forecast had been in the 1960s. Real progress. But there was always this ceiling, this frustrating limit where forecasts beyond about a week just fell apart. They became no better than climatological averages, basically just saying, well, it's January in Chicago, so it'll probably be cold. And Lorenz had explained why. The atmosphere is a chaotic system. Small errors in your initial measurements, and there are always errors because you can't measure the temperature and wind speed at every single point in a continuous fluid. Those small errors grow exponentially over time. Your single deterministic forecast, no matter how good your model is, will inevitably diverge from reality. Now, here's what's really clever. Instead of throwing up their hands and saying, well, chaos means we can't predict the weather, meteorologists did something much more creative. They said, okay, if the problem is that we don't know the initial conditions perfectly, and small differences in initial conditions lead to very different outcomes, then let's not make just one forecast. Let's make 50 or 100. Each one starting from slightly different initial conditions, each one representing a plausible version of what the atmosphere might actually look like right now, given the uncertainty in our measurements. This is ensemble forecasting, and it's one of the most important practical applications of chaos theory in existence. The idea was developed in the late 1980s and early 1990s, and two groups implemented it almost simultaneously. At the European Centre for Medium-Range Weather Forecasts, ECMWF, based in Reading, England, a team led by Tim Palmer developed their ensemble prediction system, which went operational in 1992. And at the National Centers for Environmental Prediction in the United States, Zoltan Toth and Eugenia Kalnai developed a similar system that also launched in 1992. Both groups were directly inspired by the insights of chaos theory. Both understood that the right response to sensitivity wasn't despair, but probabilistic thinking. Here's how it works in practice. You start with your best estimate of the current atmospheric state. Then you perturb it. You create dozens of slightly different versions, each one tweaked in ways that are consistent with the known uncertainties in your observations. Maybe the temperature over the North Atlantic is half a degree warmer in one version, or the jet stream is shifted slightly south in another. Each perturbation is small, plausible, within the range of what your instruments can't quite pin down. Then you run your full weather model forward from each of these slightly different starting points, and you watch what happens. For a 1-day or 2-day forecast, all 50 runs will probably agree pretty closely. They'll all show roughly the same weather. That tells you the forecast is reliable. The atmosphere isn't in a particularly sensitive state right now, at least not for the next couple of days. But go out 5 or 6 days, and the runs start to spread apart. Some show rain on Saturday, others show sunshine. Some develop a storm system, others don't. The degree of spread in the ensemble tells you something incredibly valuable. It tells you how confident you should be in the forecast. A tight cluster of ensemble members means high confidence. A wide spread means genuine uncertainty. And this is where chaos theory's deepest lesson gets translated into something you can actually use. The forecast isn't a single number anymore. It's a probability distribution. There's a 70% chance of rain on Thursday. There's a 30% chance that the storm will track north of the city instead of south. That probabilistic framing, which might seem obvious to you now because you're used to seeing percentage chances of rain on your weather app, was a genuine conceptual revolution in meteorology, and it came directly from understanding chaos. Think about what that means for a moment. Lorenz's discovery in 1961 seemed like bad news. It seemed to say, prediction has a hard limit, and there's nothing you can do about it. But the mature response, the response that took decades to develop, was to say, yes, prediction has limits, but we can quantify those limits. We can tell you not just what we think will happen, but how sure we are. And that turns out to be far more useful than a single confident forecast that might be wrong. Tim Palmer, who was instrumental in developing ensemble forecasting at ECMWF, has talked about this beautifully. He's described how the key insight was recognizing that the initial condition uncertainty isn't a nuisance to be eliminated. It's information to be exploited. By sampling that uncertainty systematically, you learn about the dynamics of the atmosphere itself. You learn which situations are inherently more predictable and which are inherently less so. Some atmospheric configurations are relatively stable. The ensemble members stay together for a long time. Others are right on the edge of a bifurcation, where tiny differences determine whether a storm develops or doesn't. The ensemble tells you which regime you're in, and the technique keeps getting more sophisticated. Modern ensemble systems don't just perturb the initial conditions, they also account for uncertainties in the model itself. Because no weather model is perfect, they all make simplifying assumptions about how clouds form, how radiation interacts with the atmosphere, how turbulence works at scales smaller than the model's grid spacing. So modern ensembles also vary these model parameters, or even run multiple different models to capture that additional source of uncertainty. The result is a richer, more honest picture of what the future atmosphere might do. Now, here's something that connects back to those Lyapunov exponents we talked about earlier. Remember, a Lyapunov exponent tells you the rate at which nearby trajectories diverge in a dynamical system. The atmosphere has positive Lyapunov exponents. That's what makes it chaotic. And the magnitude of those exponents effectively sets the timescale over which prediction skill decays. For the mid-latitude atmosphere, the dominant Lyapunov exponent corresponds to an error doubling time of roughly 2 to 3 days. That means whatever error you start with in your initial conditions roughly doubles every couple of days. And since your initial errors aren't zero, they're finite, determined by the density and accuracy of your observation network, there's a time horizon beyond which the errors have grown so large that your forecast has no skill left. Lorenz estimated this theoretical limit at about 2 weeks, maybe 10 to 14 days, depending on the situation. And remarkably, that estimate has held up pretty well. Modern weather forecasts do show genuine skill out to about 10 days on average, sometimes a bit further for large-scale features, sometimes less for small-scale details, like exactly where a thunderstorm will pop up on a summer afternoon. The improvement in forecast skill over the decades has come not from somehow defeating chaos, you can't, but from reducing the initial errors through better observations, denser observation networks, satellite data, and better data assimilation techniques that combine observations with model predictions more intelligently. Every time you reduce the initial error, you buy yourself a little more time before chaos takes over. But you're always running on a ticking clock. And this is where it gets really practical, where it touches your actual life in ways you might not realize. When a hurricane is approaching the coast, forecasters don't just run one model and point to a single track on the map. They run ensembles, dozens of simulations. And what you see on the news is that cone of uncertainty, that widening cone showing where the hurricane might go. That's essentially a visualization of ensemble spread. The cone is narrow in the near term because the ensemble members agree, and it widens as you go further into the future. because the members diverge. That cone is chaos theory made visible. It's Lorenz's discovery, operationalized, turned into something that helps emergency managers decide which counties to evacuate. The same probabilistic thinking has spread far beyond weather. Climate science uses ensemble methods extensively, not because climate is unpredictable in the same way weather is, but because there are uncertainties in how the climate system responds to forcing like greenhouse gas increases. You run many simulations with different model configurations and different assumptions, and the spread tells you about the range of possible futures. Hydrology uses it for flood forecasting. Aviation uses it for turbulence prediction. Energy companies use ensemble weather forecasts to predict wind and solar power generation. The whole framework of probabilistic prediction that chaos theory inspired has become infrastructure, invisible, essential, woven into decisions that affect millions of people. And there's something philosophically satisfying about this, if you think about it. Chaos theory started as a discovery about limits, about what we cannot know, what we cannot predict, no matter how hard we try. And that's real. That limitation is genuine and permanent, but the human response wasn't to accept ignorance. It was to get smarter about characterizing what we don't know, to turn uncertainty itself into useful information, to say, I can't tell you exactly what will happen, but I can tell you the shape of what might happen and how likely each possibility is and where the boundaries of my knowledge lie. That's a profound shift in how we think about prediction, and it reaches into areas you might not expect. Because chaos theory's influence didn't stop at weather and physics and biology. It seeped into mathematics itself, into the way we think about computation, into questions about what it means for a system to be complex. And one of the most fascinating threads, one that connects chaos to some of the deepest questions in modern science, involves a concept that sounds deceptively simple: the edge of chaos. There's this idea, explored extensively in the 1990s and still debated today, that the most interesting, most computationally rich, most lifelike behavior tends to occur not in orderly systems and not in fully chaotic ones, but right at the boundary between the two. And the person who did more than anyone to crystallize this idea was working not at a university or a government lab, but at a brand new institution in the desert of New Mexico, a place called the Santa Fe Institute, where a remarkable group of scientists from wildly different fields had gathered in the mid-1980s with an ambitious and somewhat vague mission: to build a science of complexity. To build a science of complexity itself, not physics, not biology, not economics, but the study of how complex behavior arises in all of these fields and what, if anything, the patterns have in common. The Santa Fe Institute was founded in 1984, and its origins are a story worth lingering on for a moment, because they tell you something about the mood of science at that time. The driving force was George Cowan, a physicist who'd spent decades at Los Alamos National Laboratory. Yes, the nuclear weapons lab, the one built during the Manhattan Project in the mountains of New Mexico. Cowan had seen firsthand how the most powerful scientific breakthroughs came when people from different disciplines actually talked to each other. Physicists talking to mathematicians, talking to engineers. And he looked around at the academic world of the early 1980s and saw the opposite: increasing specialization, departments that barely communicated, brilliant people solving narrow problems in isolation. So he gathered a group of senior scientists, including several Nobel laureates, Murray Gell-Mann from physics, Philip Anderson from condensed matter, Kenneth Arrow from economics. And they hatched this plan for an institute with no departments, no tenure, no permanent faculty in the traditional sense. Just a place where people could come together and work on the big, messy, interdisciplinary problems that didn't fit neatly into any one field. And complexity was the word they kept coming back to. What makes a system complex? Not just complicated. A jet engine is complicated, but we understand it. We designed it. Every part has a purpose we specified. Complex is different. Complex is an ant colony, where no individual ant understands the colony's behavior, but the colony as a whole does remarkably sophisticated things, building structures, farming fungus, waging wars, adapting to threats. Complex is an economy where millions of individual decisions somehow produce emergent patterns that no one planned. Complex is the immune system, the brain, an ecosystem. And the question the Santa Fe Institute was asking was, is there a shared science underneath all of these? Are there universal principles that govern how complex behavior emerges from simple components, the way thermodynamics governs heat flow, regardless of what specific substance you're heating? Now, here's where chaos theory connects to this bigger story. One of the key figures at Santa Fe in those early years was a mathematician and computer scientist named Christopher Langton. Langton had a remarkable personal story. He'd been a serious rock climber, had a near-fatal hang-gliding accident in the late 1970s that left him in the hospital for years, and during his long recovery, he became obsessed with the question of what makes something alive. Not in a mystical sense, but computationally. What is the minimum set of rules that can produce lifelike behavior? He got into cellular automata, those grid-based computational systems where each cell follows simple rules based on its neighbors, and patterns emerge over time. The most famous example is John Conway's Game of Life from 1970, where just 4 simple rules produce an astonishing zoo of behaviors: gliders that move across the screen, oscillators that pulse, structures that grow and replicate. Langton started systematically exploring what happens when you vary the rules of cellular automata, and what he found was striking. Some rule sets produced completely static, frozen behavior, order. Other rule sets produced completely random, structureless noise, chaos, essentially. But right at the boundary between these two regimes, right at the transition point, he found something else entirely. He found the most complex, most interesting, most computationally rich behavior. Structures that could store information, transmit signals, perform computation. The kinds of behaviors that looked, if you squinted, a little bit like life. And this is what became known as the edge of chaos. The idea that complex adaptive systems, living things, evolving populations, maybe even consciousness itself, tend to exist at this critical boundary between too much order and too much randomness. Too much order and you're frozen, rigid, unable to adapt. Too much chaos and you're noise, unable to maintain any structure at all. But right at the edge, you get this remarkable sweet spot, where the system is stable enough to maintain coherent structures, but flexible enough to adapt and evolve and compute. Think about that for a second. Think about your own brain. If every neuron fired in perfect lockstep, total order, you'd have a seizure. If every neuron fired randomly, total chaos, you'd have noise, no thought, no consciousness. But your brain operates somewhere in between, in this regime where patterns form and dissolve, where information flows and gets processed, where stability and flexibility coexist. There's actually good evidence, accumulated over the last couple of decades, that healthy brain dynamics sit near this critical boundary. And when they don't, when the brain tips too far toward order or too far toward chaos, that's when pathology emerges. Now, I should be honest with you about the edge of chaos idea, because it's one of those concepts that generated enormous excitement in the 1990s and then faced serious scrutiny. The original claims were broad and ambitious. Stuart Kauffman, another Santa Fe Institute luminary, a biologist and theoretical thinker, argued in his 1993 book, The Origins of Order, that natural selection itself tends to push biological systems toward the edge of chaos, that this is a deep principle of self-organization that complements Darwinian evolution. That's a big claim. And while the basic observation is real, critical transitions between order and chaos do exist, and interesting behavior does tend to cluster near them. The strong version of the theory, the idea that this explains the origin and organization of life, remains controversial. Some of the early results turned out to depend heavily on the specific models used. The universality that people hoped for hasn't been established as firmly as, say, Feigenbaum's universality in period doubling cascades. But here's what's genuinely lasting about the idea. It connects chaos theory to something much larger, the study of phase transitions and critical phenomena in physics. Physicists have known since the mid-20th century that remarkable things happen at phase transitions. When water is right at the boiling point, for instance, you get fluctuations at every scale, tiny bubbles and enormous ones, correlations that span the entire system. The mathematics of critical phenomena, developed by people like Leo Kadanoff and Kenneth Wilson in the 1960s and 70s, shows that systems at critical points exhibit scale-free behavior, power laws, self-similarity, the same kinds of fractal structures that Mandelbrot found everywhere. So the edge of chaos idea was really connecting chaos theory and fractals to the much older and more established physics of phase transitions. And that connection has held up. It's one of the genuine deep threads in modern science. And this brings us to where chaos theory lives today, in the 21st century. Because the field has matured in ways that are both humbling and beautiful. The initial excitement of the 1980s, the sense that chaos theory was going to revolutionize everything, that we'd found a new paradigm, that settled down, as we talked about earlier. The overselling got corrected. But what remained, what's still growing, is a set of genuinely powerful ideas and tools that have woven themselves into the fabric of modern science and engineering so thoroughly that people sometimes use them without even thinking of them as chaos theory. Take machine learning and artificial intelligence, for instance. When you train a neural network, the optimization landscape, the space of all possible configurations of weights and connections, is extraordinarily high-dimensional and full of complex structure. There are valleys and ridges and saddle points, and the training process is navigating this landscape, trying to find good solutions. Understanding the geometry of these landscapes, understanding which regions are stable and which are sensitive to perturbation, understanding how information flows through the layers of a network. All of this draws on ideas from dynamical systems, theory, and chaos. Recurrent neural networks, the kind that process sequences like language or time series, are literally dynamical systems, and their behavior can be analyzed using Lyapunov exponents and attractor theory. The vanishing gradient problem that plagued early recurrent networks, where information about the distant past gets lost as it propagates through the network, that's essentially a stability problem in a dynamical system, and recognizing it as such helped lead to architectures like long short-term memory networks that solved it. Or take climate science, which we touched on with ensemble forecasting, but which goes much deeper. Climate is not weather. Climate is the statistics of weather, the long-term patterns, the averages and variabilities and extremes. And one of the profound insights from chaos theory is that you can have a system where individual trajectories are unpredictable, but the statistical properties of the attractor are stable. The weather on any given day in March is unpredictable more than 2 weeks out. But the fact that March in New York is colder than July, that's a property of the attractor, and it's robust. Climate models aren't trying to predict the weather on June 15th, 2087. They're trying to characterize the attractor. To understand how the statistical properties of the climate system change when you alter the boundary conditions, like increasing greenhouse gas concentrations, and that's a legitimate thing to do, even in a chaotic system. It's the difference between asking, where exactly will this particular trajectory go, which chaos theory says you can't answer long-term, and asking, what does the set of all possible trajectories look like, which you often can answer. That distinction, which comes directly from the mathematics of strange attractors, is crucial for understanding why climate projection is possible, even though weather prediction is limited. And here's something that might surprise you. Chaos theory has become important in engineering, not just as a thing to worry about, but as a thing to exploit. There are communication systems that use chaotic signals, because chaotic waveforms are broadband, noise-like, and hard to intercept. They're actually useful for secure communications and radar. There are mixing devices that deliberately induce chaotic advection, the stretching and folding of fluid elements. Because chaotic mixing is far more efficient than turbulent mixing for certain applications, like mixing viscous polymers or blending pharmaceutical compounds. There are even proposals for chaotic computing, using the sensitivity of chaotic systems as a feature rather than a bug to explore solution spaces more efficiently than conventional algorithms. But maybe the deepest legacy of chaos theory is philosophical. It changed what we think determinism means. Before Poincaré, before Lorenz, determinism and predictability seemed like the same thing. If the universe follows precise mathematical laws, and it does, at least at the scales where quantum mechanics doesn't dominate, then in principle, you should be able to predict everything. Laplace's demon, remember? Give me the positions and velocities of every particle, and I'll tell you the future. Chaos theory showed that this is wrong, not because the laws are imprecise, but because the information required for long-term prediction is, in practice, infinite. You'd need to know the initial conditions to infinite decimal places, and you can't. Not because your instruments aren't good enough, but because there's a fundamental limit. The sensitivity to initial conditions means that any finite measurement, no matter how precise, will eventually diverge from reality. And that's not a failure of science. That's a discovery about the nature of reality itself. The universe is deterministic in its rules, but unpredictable in its outcomes. And that's not a contradiction. It's a deep truth about what it means for something to be complex. It means that novelty is genuine. The future isn't just the past rearranged in predictable ways. Deterministic systems can generate authentic surprise, can produce patterns that are forever new, trajectories that never quite repeat. The strange attractor, remember, is a fractal. It has infinite structure at every scale. A trajectory on a strange attractor wanders forever without repeating, always finding new paths through the same bounded region of space. There's something almost poetic about that. Bounded but infinite, determined but unpredictable, constrained but endlessly creative. And lying here thinking about all of this, from Poincaré's frustrated calculations about 3 gravitating bodies to Lorenz's printout that was off by 1,000th, from Mandelbrot measuring coastlines, to Feigenbaum counting period doublings at Los Alamos. From the Santa Cruz kids building strange attractors out of dripping faucets, to Palmer running the first ensemble forecasts at the European Center. What strikes me is how human the whole story is. These weren't abstract discoveries handed down from on high. They were made by people who were confused, who followed hunches, who got rejected by journals, who stayed up too late staring at computer screens, who saw patterns that nobody else could see yet. Lorenz wasn't trying to discover chaos. He was trying to understand the weather. Mandelbrot wasn't trying to invent fractals. He was trying to understand cotton prices. May wasn't trying to revolutionize dynamical systems theory. He was trying to understand fish populations. The deepest discoveries came from people who were paying close attention to the world and who had the courage to take seriously the things that didn't fit the existing framework. And that's maybe the most comforting thought to drift off with. The universe is wilder and more creative than we once imagined. The simple equations that govern falling apples and orbiting planets also generate infinite complexity, patterns within patterns, structure at every scale, surprises that never end. And we figured that out. Not all at once, not without wrong turns, but steadily, over a century of patient, curious, sometimes stubborn human effort. The same sensitivity that makes the weather unpredictable makes the world endlessly interesting. The same mathematics that limits our forecasts reveals the hidden geometry of clouds and ferns and heartbeats and galaxies. And right now, somewhere, someone is staring at a computer screen late at night, watching a simulation do something unexpected, something that doesn't quite fit the theory, and they're leaning forward, and they're thinking, "That's strange. That's interesting. I wonder why it does that." And maybe, if they follow that thread long enough, they'll find something beautiful waiting at the other end. The way Lorenz did, the way Mandelbrot did, the way all of them did. But that's a story for another night. For now, just let the patterns fold and unfold in your mind. The stretching and folding, the infinite structure in finite space, the quiet, determined creativity of a universe that never quite repeats itself. And let that carry you, gently, all the way to sleep.